Welcome to another in this series where we look in depth at how a diode laser works. Now, in the last session I promised that I would upgrade this machine from 5 watts to 10 watts, but I've decided to change my mind. Now, I was rather disparaging about this little 5 watt laser. What? 5 watts? What can you do with 5 watts? Can't even blow a smoke ring. I think it's got a lot more potential than I ever gave it credit for. So, my mistake. There's a lot of people out there that struggle to do engraving on wood or on acrylic or glass with a 5 watt laser. I don't necessarily think it's a real problem. You need to understand several things about the materials and about the laser beam itself. I'm not even going to consider whether this is a diode laser or not. The laser beam and how you focus the energy is the most important part of damaging material, even with the very small amount of power like 5 watts, which I laughed at. I'm not laughing quite as much now. Today we're going to do a few experiments with some of these materials that supposedly don't mark, and we'll find out just what marking these materials is all about. Now, one of my first attempts at looking at the beam was using a piece of poplar plywood. Now, poplar plywood is very nice and white. If you remember back to the colour theory that we talked about in the earlier sessions, you'll know that white is not really a colour at all. It's a mixture of colours. All the colours of the rainbow, when they mix together and hit our eye, we perceive all those colours mixed up as white. So white is not a real colour, it's a colour that our brain has created for us, in the same way that black is not a real colour. Black is the absence of any colours of the rainbow, full absorption of light. Secondly, I must tell you that the colour white is not the only problem here. Wood is made of cellulose. And again, if you remember back to one of the earlier sessions, I spoke about the spectral absorption of wood. At 455 nanometers, its absorption is almost that, nothing. Almost nothing. But that means that with very little power, we shouldn't really be able to damage wood at all. Because A, it's white, and B, it doesn't absorb the light. So we're on an absolute loser to start with, surely. And what I'm planning to do is to try and scorch this wood. Okay, as you can see, we've got a graded scorch on there, from quite dark to pretty light. It's amazing how noisy this little diode laser is. For doing half of nothing, it's making a hell of a noise, isn't it? But I'm going to try and make a pencil mark here, roughly in line with where I think the pattern will be. So we're going to be running this at stupid speeds and stupid powers. I'm going to be running at only 30%. I'm going to be running at 400 millimeters a second. So the exposure time for every one of these dots and dashes is incredibly small. Let's go on to the really dark bit at the edge. And then we'll try and move to this section here, which is light brown. So somewhere on there are 3 patterns. Let's go and look at them under the microscope. I've got the magnification set very low on this at the moment. It will be obvious if we see any straight lines. I purposely set the wood so that the grain was vertical, which means our pattern is going to go across the grain and it's going to be very obvious if there's a pattern there of any sort. There's my pencil mark. Let's move in a little bit, and I think it'll be pretty obvious if there's any marks across that wood grain. So we've got 3 parameters here. 1, the wood is white, so it's going to reflect any beam. Secondly is wood, which is cellulose to the extreme, and so the absorption capability of our power is going to be virtually nil. And then thirdly, we're running at 400 millimeters a second with only 30% of 5 watts. Exposure time, half of nothing. So look, we got what we expected, nothing. So here we are, we're moving across the wood into a slightly more scorched area. And wow, so the first thing we can rule out is exposure time. There's plenty of exposure time. We're still running at 400 millimeters a second to 30% power, and we're marking the same wood, just a few millimeters further across. The only difference is the colour. It's changed from white to sort of a scorchy brown. Look at the texture of that wood. Have I burnt any of it away when I compare it to this white wood? Texture wise, it looks exactly the same. So first question is, why is that wood turned brown? Because I don't think I've changed the chemistry much, maybe slightly if you're a chemist, but the cellular structure is exactly the same. What's really happened is I've changed the ability of the wood to reflect all the white light. Now, because the background is brown, it's absorbing light, even the blue light. And so consequently, the blue light is now able to do damage to this non-white surface. How much damage are we doing? Well, let's just zoom in a little bit and let's hunt for a line, shall we? Oh, there it is. Look, there's a line. So there's the surface of my material. You can see the cellular structure there, the tubes of cellulose. And then we'll start gradually moving down into the, and about there is the bottom of the cut. So let's zoom out again. But just before we get to the surface, you'll notice just here, we've got wood grain, which has got some depth to it. And then we're back to the surface. So let's look at that with a slightly lower magnification. Some nice surface wood grain there, and go into the bottom of the groove. There we go. So there is some depth to that cut. But the interesting thing is, if we move to the surface, what do we see? We don't see any black marks along the edge here. When we look at it in that magnification, why are those marks black? Have we burnt black marks into that surface? We've cut deep grooves into that surface, which we weren't able to do when it was white. So brown has allowed us to break through the surface and start a cutting process. Although I'm engraving, I'm cutting into the material with that line at high speed. Why? Well, that really, I think, probably tells us quite a lot about the cutting process that we're going to be looking at some stage in the future. That mark there, from there to there, is 0.1 of a millimetre. And that line there, maybe it's around about 0.03 or 0.04 wide. So that's a very, very thin, high intensity point of energy that we're firing at that material just there. I know we've got 5 watts, but remember what I keep stressing. We don't cut or damage with watts. We damage and cut with intensity. And remember what intensity is. If we take an area and we squeeze millions and millions and millions of photons into the area, we have a very high photon density. We have the potential to do a lot of damage, a lot of stimulation of the molecules. And that's what we've done there. We've stimulated just that very thin line of molecules with a very, very high intensity. Let me ask you a question. I've got a certain amount of strength. Would you rather I poked you on the back of your hand with that end of the thermometer or that end of the thermometer? Which would hurt more? I've concentrated all my capability, all my pressing capability into a very small area. You feel it as doing a lot of damage. Well, that's exactly what the material feels. If we can squeeze more and more effort into a smaller and smaller area, the intensity of that effort goes up by an amazing factor. If it's a point, it's virtually zero area. And if you put any energy into zero area, its intensity is going to be nearly infinite. There's test number 3. Still doing the impossible. We're marking wood at 400 millimeters a second. The only difference this time is we've got a slightly lighter scorch in the background. Let's have that one because it happens to be right on top of a strand of cellulose. Remember what I talked about last time, being an air crash investigator. You mustn't ignore anything. You must look at everything and make as many observations as you possibly can from the facts that you know. Well, I'm aware that one of the facts about a diode laser is it doesn't switch on and off instantly. I think it switches on faster than it switches off. The light takes a certain amount of time to switch off. So there is what they call a recovery off time. And what we can deduce from that, I believe, is that we can see which way that mark was made, which direction the beam was going. And I think the beam was going this way, because let me change the focus a little bit. And look out here. Can you see these black marks? So I think the beam started here, and then it very quickly got up to power here and dropped down to maximum depth, full power, just there. Okay, and then it went as deep as possible for a short period of time, and I'm trying to find out where that is. We can come towards the bottom here. Look, we can see the bottom. By changing the focus, I can find the bottom. It probably switched off about there, but then carried on for this little bit here. So it took time to switch on at the beginning of the black pixel, and by the time it had got to maybe a third of the way across the pixel, it was full power. And then it got to the edge of the pixel here, where it was told to turn off, and then there was a little bit more that was here, overhanging the edge of the pixel. But hang on, it wasn't actually overhanging the edge of the pixel, because although the pixel told it to turn on here, it didn't start burning until a third of the way across the pixel. So effectively what we've got here is 1 pixel width, even though it didn't start and finish when the pixel said start and finish. We've got this black frilly bit around the outside here, which looks like a little bit of carbon. If we take a look in here, we'll see that, let's just zoom in and out a little bit. If we can go in and out a little bit, it's difficult to do that. We can just see here, look, as we start to go in, it's still not black. It's not carbon. And look, when we go into the bottom here, I've got the light in there. That's not carbon either. I'm proposing to you that there is enough intensity in that beam at that point that what's actually happening, it's so intense that it's going through a process, which I will explain in a minute, where it's actually vaporizing the material. And I also know that by the amount of table movement that I was making to the microscope, that cut to get it out of focus is not as deep as test number 2. So what the hell is going on? The first test, we couldn't find any impression at all. The second test was quite a deep impression. And the third test was a shallower, but still an obvious mark. Would anybody like to stand up in front of the class and explain what we've just seen? Let me tell you that what you're seeing is not what you believe you're seeing. They are not brown lines. They happen to be brown because of some external light is illuminating part of the internal depth. So we appear to have almost black marks there. Not quite black, because look, you can see what black is here. Why are they a different colour to test number 2? Okay, we couldn't see test number 1 for all the reasons I explained. But we can see test number 2 and test number 3, because I've changed the colour of the background that we started with. I haven't changed the chemistry of the wood. It still looks exactly the same. What I have done is change the molecular structure somehow in the wood so that it is actually transmitting now brown light as opposed to white light. So I haven't explained to you why the colour difference of the background is having such a significant effect. Let's concentrate on this question. Why is that black and the other one is light brown? Same laser beam, same power, same exposure time. Why different colours? Remember what black is. Absorption of colour. That line appears to be absorbing all the light. The only reason you can see the surface is because, look, I've put light on the surface. If I take the light away, you can't see the surface. So light is a very key factor in being able to see what's in that very, very deep trench there. If you can't get any light into the trench, it looks black. It's not black in that trench, I can assure you of that. It's this colour. Because we've vaporised the material and we've left a nice clean wood material on the surface of those cuts. I can hear you laughing and saying, yeah, you expect us to believe that? Well, I'm going to cut a little piece of video in now that I took when I was talking about this same subject using a CO2 laser, which has got a very sharp, very sharp point on it, which allows vaporization of the wood, the cellular structure. This one is the raw beam, and this one has been passed through a 2.5-inch lens to concentrate it. It's the same beam running at the same speed with the same amount of power in the profiles. It starts off at 15%, 25%, and goes up to 95%. Now, apart from the fact that we can see a significant difference in the line width at low power, and you'll notice that the line width does subtly get wider as the power increases. It's much more difficult to see it when it's passed through a lens, but it is there. But as the lines get thicker, they're not changing the blackness, they're all exactly the same colour black. Why would that be when we're increasing the power? So why is this dark brown and why are these black? Now let's just have a look at the edge if I can. They are cuts, even at 15% with that thin line. Look how deep we've managed to cut the very first line. I'm now going to change the speed. At the moment it's about somewhere just over halfway. So if I reduce the speed, because I can't change the power, I've already got the power in this pattern set up to 100% at the top here nearly. Now that one was 50 millimeters a second and this one was 30 millimeters a second. The lines here are slightly thicker, but I wouldn't know that till I looked at them under the microscope and measured them exactly. We've seen the change of line thickness with power. There is also going to be a thickness line change with speed as well, but it's more subtle. The question really I'm going to ask you now is, what's the difference in colour between those two samples? They're all roughly black, as opposed to brown when we had no lens in. Are your eyes deceiving you? Are they really black? Let's just have a look. It's very definitely black. Or is it? Let's take the next one off. It's not black, but I can make it black by doing that. It's an optical illusion. If you can't get light into somewhere, you can't reflect the true colour of what's inside. Your eyes are deceiving you. These black lines are not black at all. We can't damage this structure because it doesn't absorb light. Well, it absorbs light at the CO2 wavelength, which is why it's much easier to see. But I can tell you that this is doing exactly the same thing even at 455 nanometers. It's vaporizing this wood. We've found a mechanism here by which we can influence the rate at which damage occurs. Magically, we've made it cut. How does this work? You saw me with my heat gun, how difficult it was to actually turn this material into a scorched material. But if you use a blow lamp on wood, you know how quickly you can turn the surface from brown to black. And what's that black? Carbon. And what does carbon do? Well, first of all, carbon is black, so it sucks in the energy, and B, it is very easily vibrated by a huge range of wavelengths of light. And even down at 450 nanometers, carbon is very easy to excite. So it sucks in the energy once you can get carbon into your surface. Now, I've not got carbon into this surface, but what I've done, I've changed the colour. And changing the colour means it starts to absorb light energy. And once I can start to absorb light energy, I will start to produce a scorch which is more than just this dark brown. So now we've started a process off where we're scorching the surface and we're destroying the cellular structure, and what's left over, because of the surface structure, even at 400 millimeters a second, which is what we did this, we were able to burn a deepish groove in there, purely because we started off the process of burning with this faint brown colour. Once we can suck energy into the surface because of the colour, not because of the structure of the material, then we can start the process of damaging this material. I absolutely love it when people tell me it's impossible to do something, because if you understand what's going on, most things are possible. Not everything, but most things. And here we've got a transparent material, which everybody tells me the laser beam will pass right through it. You can't engrave on the surface. Let's try this. Well, as I said at the beginning of this video, I'm surprised at what 5 watts will do. In fact, let me rephrase that. This is 40% of 5 watts, which is only 2 watts at 140 millimeters a second. And it's acrylic, and it's clear. And I've done something with it. It's not on the surface, it's not on the bottom, but if we look carefully, you'll see that it's inside the material. Interesting question, isn't it? What have I done? Oh dear, how do I begin to explain this? I've set the focal point to halfway into that material. And you've seen how intense the focal point is. Most people set the focal point on the front or the back surface. So blue will pass right through glass like all the other colours of the spectrum. Now, even though we've only got 5 watts of light here, we've actually managed to focus that light down to a very, very small point, as I've demonstrated in the previous videos. We've got incredibly high intensity at the intensity focal point. Now, the intensity focal point might not be, and probably isn't, the optical focal point. And what's actually happened there, because this material is transparent, what it basically means, there's lots and lots and lots of space between the atoms in this material. You've got to go back to the picture of the atom that I used in the first diagram. The atom is 99% space, and there are electrons floating around the outside of it. Electrons don't really absorb the energy very well, and what we're achieving there is direct hits on the centres of the atoms, the core of the atoms, the protons and the neutrons in the centre of the atom, and they are absorbing the energy. Acrylic is vaporising and turning to steam. So you've got little explosions that are taking place inside there, producing little gas bubbles. Now if you put those gas bubbles too close to the surface, then they will break out and they will make a real mess of your surface. But if you can keep them enclosed with just enough power to create the bubbles inside the actual acrylic itself, then hey, you get this wonderful effect. Okay, it's not perfect, but it's a very interesting effect, isn't it? And normally you cannot engrave acrylic because it is transparent, and the only way that you can damage the surface of acrylic is by some sort of energy transfer mechanism. Now this is not an energy transfer mechanism, this is just raw acrylic, as you saw. There was no tricks involved. Now look, here we've got 2 kindred spirits. We've got some water here, and we've got some acrylic there. Now these two, although this is a unique plastic, there is only one plastic that does what acrylic does. It is very similar to water, in that you freeze this stuff below 0 degrees C and it becomes solid, just like this. And provided you can stop the air bubbles forming in it, it is crystal clear, like this, but bluish. When you take this stuff above 0 degrees C, look, it's liquid. And if you take this stuff above 160 degrees C, it's liquid. But if you take this to 100 degrees C, it boils and produces steam. If you take this to 200 degrees C, it boils and produces acrylic vapour, just like steam. So these are kindred spirits. And in the same way, that if I've got this in its liquid state, which I have now, and I do something to it, magic happens. Look, you can see through this at the moment because it's crystal clear. It's water. You can see through it. Okay? But if I do this to it, magic happens. Look what I've done. I've turned it white. Now, how did I turn that white? I didn't do anything to it magical. All I did was add air bubbles to it. And that's what happens when you engrave acrylic. If you want to make it white, you have to make it so that it's in its liquid state, boils, and then you have to freeze it quickly before the bubbles disappear and it becomes clear again. So that's the trick to making proper engraving on acrylic. Now there is another way that you can sort of appear to be doing engraving on acrylic. Now I'm going to put a scratch in the material. I've disturbed the surface of the material so that it's no longer transmitting the light. That's effectively the way that you engrave acrylic. You damage the surface in some way. You can just damage the surface and you can sort of make a very faint acrylic mark. So engraving acrylic is all about damaging the surface. Ideally, to get the whitest engraving and the most dense engraving, you need to produce bubbles on the surface. And to do that, you've got to raise the temperature above 160 degrees C. The trick, which most people do, is they put something on the surface. And the something that goes on the surface is normally black, because black absorbs energy. And what we're trying to do, we are trying to absorb energy, but we're trying to absorb it in a way that allows the heat to transfer very quickly from the surface film to the material underneath, so that we can boil the material underneath. Now the usual approach is to put something like a tempera paint. It just so happens that I have some carbon black here. Soot, basically. Elegant soot. And here it is. Now I'm not going to make up a tempera mix. That's one of the concoctions that Michelangelo and Leonardo da Vinci, etc. used to use in their paintings. This is soot, and soot is carbon. And hey, remember, I've already talked about the amazing properties of carbon. So if we can put a thin film of carbon on the surface, not a thick film of egg yolk and this stuff, because that's going to absorb the energy and stop it from going into the surface. Yeah, it will have an effect, but what we want to do is we want to transfer this stuff, which sucks in the heat, and we want to transfer it to the surface of this material as quickly and as elegantly as possible, so that we damage this material to some great extent. Okay, now let's give this a try. Okay, now that was soot, remember, and you can see it's a bit streaky, but that's because I didn't apply it very evenly. But that's not the purpose of the exercise at the moment. It's the demonstration, the principle that we're interested in. So what I'll do, I'll just go in and wash that off underwater, because it's only soot after all, and we'll see how good that has come out. That's interesting because we've actually got two effects there. Look, we've either managed to catch it as a very nice positive engraving. If you put something white behind it, look, it's very definitely black. Okay, so we've changed the parameters a bit for this one. I've made the black film a little bit thicker. I've left the speed at 200 millimeters a second, and we've pushed the power up to 80% on this 5-watt diode. So we're now putting 4 watts of energy into this engraving. Single direction mode, it's not bi-directional, purely because I haven't bothered to set the scanning offset up. So running it in unidirectional mode obviates the need to set the scanning offset. So I've actually damaged the surface, which is what I'm trying to achieve. I've actually engraved into the surface. So let me go and check out what we've done. Well, I think you can see that's a pretty positive type of engraving this time, because I think we've pushed right through the black and we've managed to carry on with the damage to the acrylic surface. So we'll go and look at all my bits and pieces under the microscope and see what we've produced.
With my crash investigator's hat on, I look at this and I'm not amazed by what we've produced. What I'm interested in is what's actually going on here. How have we managed to produce that? Well, we've managed to focus the energy down to a very, very sharp point inside the material, and we've managed to hit some molecules and do some damage to them. We've managed to excite 1 or 2 molecules in there because there's not many of them. They're very well spread out. There's lots of space. But we've managed to target 1 or 2 of the molecules and we've hit them. And what have we done? Well, we've made some carbon. How can we make carbon? This is acrylic. Methyl acrylate, which is the basic molecule that makes up acrylic sheet. And what we find is we've got lots of carbon, we've got hydrogen and some oxygen. What we've done, we've probably managed to shake the molecule in such a way that we've separated the carbon. Well, actually, I reckon it's the oxygen and the hydrogen that have actually created the little explosion, as we shall see when we put this under the microscope. So my questioning nature always asks, how did that happen? What have I just seen? I don't just look at the end result. In this instance, well, look, we've got this black product which has happened on the surface. It looks as though we've probably melted a little bit of the carbon into the surface. There's no indication of any surface damage there at all. And then finally this one, well, we've put the same amount of carbon on the surface, but we've managed to burn through the carbon layer, and somehow, although we've got some colour there, there's also some 3D-ness to that surface. Not very much, 25 microns, 1/1000th of an inch, but that's an interesting observation with my crash investigator's hat on. Why the different colour and why the different texture?
This is only 25 times magnification. We're just looking at a sample area here, and we can see several things. First of all, in the background here, there's a black section. And look what's on that black section. You can see the scan lines. That's interesting. What we've got here is white. And remember what white is? All these colours of the rainbow uniformly mixed up that are arriving back at your eye, so you can't see the colours. All you see is the mixture of colours, white. It's telling me what's happening inside this material structure. Look at this feathery structure here. Now this is classic shear technology. What's happened is the material has basically torn apart. Now unfortunately I can't get any lower resolution than that, but we can take a look around and we can see lots and lots of little bubbles of explosions and lots of blackness. Each one of those little black areas has got scan lines on it. Now we can see that these scan lines have taken place at different depths, because look, this one is in focus and this one's out of focus. So I can bring that one in the background into focus, and there we go, and this one has gone out of focus. So these are at different depths in the material. Now we've got another interesting question that arises. This is a chicken and egg situation, and in this case you can't see the scan lines on this piece of carbon unless the carbon was there before the scanning took place. So somewhere in advance of the scan lines, which came down from the top to the bottom, we must have caused a little explosion here somewhere so that we produced this big patch of carbon, and then all of a sudden our scan lines were able to go across and mark the carbon. This sort of observation might appear to be useless, and it might be useless, but hey, you don't know whether or not this observation could lead you to something else. So don't ignore anything that you see in this picture. Look, you can see these radiating lines here. It's possible that what we might actually be seeing here is one of these little explosions, because everything is radiating away from it. You see, look here, we've got the scan lines, we've got the feathery bits, but look here, we've got a black patch which has got no scan lines on it. So this must be transparent and not carbon. Whereas this is carbon and it's picking up the scan lines. That's enough about test 1. Let's have a look at test 2. We can just see the scan lines on there. Look, the fact that I can see little blobs of white on there means I'm picking up the light from my side illumination. Let's just concentrate on that dot there. And as I move the light around, can you see the way in which it's going in and out? It's illuminating. Now, it wouldn't illuminate uniformly like that if it was a blob of solid. That is a bubble which is catching the light inside it and refracting and reflecting like a cat's eye. Because this scan line is only probably around about less than 0.1 wide, so these are very, very small bubbles. They're not big enough to create whiteness. We move on to our third one, where we put more power into it and we produced a certain amount of 3D-ness. Have we succeeded in producing bigger bubbles? because we changed the power. Let's just go and have a look at something like maybe this little block here. There's something there which has disturbed the surface and produced some little gas bubbles, but they're very, very, very small, and they're very, very non-uniform. So that's not going to produce a nice white surface for us. But hey, we have managed to produce some bubbles on the surface. We've done a little bit of boiling. Now, what we've done so far with acrylic has really not been very successful. We've really only just scratched the surface. And if you remember, just scratching the surface is not engraving. And if we can produce bubbles, then they will act like cat's eyes. They will reflect the white light in all directions, and you will get nice white engraving. To achieve bubbles, even with a CO2 laser, you can't do it with a sharp pointed beam. That focal point there will in fact evaporate the material very quickly. With a 450 nanometer diode laser, the light appears to go right the way through because it's transparent. There's a very interesting video which I'll just reference on the screen here. It shows you the problem with transparency. There isn't very much for the photons to collide with. There's huge open spaces between the protons and neutrons at the center of an atom. If we can't do it with a pointed beam, even with a CO2 laser beam, the CO2 laser beam has to be a relatively blunt beam. With a diode laser, you only have one shape of beam. You can't change the shape of the beam because you reduce the power. Remember the Gaussian distribution curve and how the shape changes with power for a CO2 laser? That doesn't happen with a diode laser. You always get a beam shaped like that, and we know we've got a beam shaped like that because we've seen how accurately and thin it can draw lines. When we focus it into halfway through a piece of material, we can manage to explode and hit a few of the atomic particles inside there and cause little explosions. The surface of this material needs to be heated up to 160 degrees C before it will turn to liquid. We then need to heat it up a further 200 degrees C before it boils, and it's only at boiling point that we manage to produce some bubbles. If we only boil the surface film on this acrylic, there's not enough depth to produce any serious bubbles. We've somehow got to get into the material enough to produce this bubbling effect. Now, I'm not sure that we've got enough power with 5 watts to be able to do that, but hey, we're going to give it a damn good shot. So here's my next strategy. Piece of clear acrylic, and I'm going to make it less clear by making the surface matte. If I can make it matte, maybe any light rays that hit that surface will tend to spread, dissipate, and not go right the way through immediately. It's a vain thought because hey, it's still acrylic. Look, I've got my carbon black mixed with isopropyl alcohol to make a cream. The chances of me being able to get this on smoothly are pretty remote, because it is a sort of a cream and I haven't got a wide enough brush here to do it. But hey, what I want is a nice thick layer of this carbon so that we've got the thickness of the carbon to heat up and maybe allow us to produce some heat in the surface. We'll just vaporise the alcohol and hopefully we've got a nice thick film of carbon on the surface there. Soot. So I've got 100% power, 100 millimeters a second, and I've dropped the focus into the material by 2 millimeters. The line interval is 0.01, so there's a huge amount of overlap on every scan line. I'm basically hoping that I might be able to induce some heat into each scan line, and so that the next scan line is reheating the previous scan line by maybe 90% or more. So I'm hopeful by these sorts of tricks that I might be able to induce additional heating into the surface and get some effect. Whether it's bubbling, I can't say. Now, while that's going on, you may be interested to know that I've looked in my sunglass collection and I've dumped my cheap shiny sunglasses, which are doing a good job of protecting my eyes from the glare. I've had no problems at all. And now I've got something which is even cheaper in my collection. I think I probably paid about £2 for these, and they're supposedly UV rated. I know that there are some nasty UV rays coming out of that blue light, and they do a great job of protecting my eyes from the glare, which is the most important thing. So I can now look at that glare and I can actually see where the actual laser beam itself is hitting. There is a red spot, a bright red spot, which indicates that the energy is being transferred into the carbon. The carbon is definitely being heated up, and occasionally you might see a little spark, a little red spark coming off there. Now it's not very uniform, the printing, purely because obviously my coating with the soot was not very uniform. It also looks a little bit knobbly and bobbly. Maybe I've produced some bubbles in there. We'll only know when we wash it off and see what we have. Okay, now this is very interesting because we can see here where my thick pieces of paint were here. It's even missed a piece there where my paint was thickest. So where the paint was thin, I have produced a depth there of 0.2. So that's absolutely amazing that 5 watts can bore into that acrylic 0.2 deep. Maybe I didn't need to mess the surface up to achieve that. Maybe I could have done it on a shiny surface. So we shall have to repeat the same thing on a piece of clear material. I don't want to lead myself or you guys astray. I need to say that what I've been using is this simulated glass. It's an acrylic with a slight green dye to it that simulates normal glass. This is just ordinary cast clear acrylic. So what I should be doing at the end of this test is running this as well. And that reads 0.2. So the surface finish didn't make any difference. I still don't think we've produced any bubbles. I think we've just produced a rough surface. I can be sure that the material I've got on here at the moment is extruded acrylic that I'm going to test next, because this is called cast acrylic, as you can see, and this is the odd piece of that material that I'm just using. I can tell that this is extruded acrylic because if you listen to the way that my fingernail drops off over the edge, can you hear that burr? Okay, let's look at the same thing on this cast acrylic. Let's just break a piece of this off and listen now. Absolutely no burr at all. And that's one of the quick and easy ways that you can tell the difference between cast and extruded acrylic when you've laser cut it. Now I don't know whether that's true for a diode laser or not. We shall have to find it out later if we can ever manage to cut acrylic. Black acrylic we should be able to cut. We know that cast acrylic works exactly the same whether it's roughed up or smooth. So let's check the same thing for extruded acrylic. You can see that, but that's engraving with a completely different colour. There's a lot more red in that beam than there is blue. Now, I'm very confident I set the focus up to the same level, surface level, but I will check it. The other thing is, maybe you've listened to it, maybe you can hear it, there's been an occasional little crack or pop. Hear it? That makes me believe the focus is wrong for this particular material. Even though it's exactly the same chemical composition, extruded acrylic has got different properties to cast acrylic. It's got a much higher melting point. This is probably up at about 250, 260 as opposed to 200. And the other thing that's obvious is we are not clearing away the soot. We're not evaporating the soot, which is puzzling. 15 plus 13 is 28. A little less intensity because we've got a slightly blunter beam. And I wonder what we've done in the way of damage. Well, I have to say that's a pretty serious engraving. That's not just a scratch on the surface, is it? Plus the fact that it's almost got like a field engraving because it's grey. We've almost melted some of the carbon black into the engraving. Yes, you see we're only down at 0.07 now. The higher melting temperature has reduced the amount of damage. Let's take a look at my green glass one to start with. Now this is a fairly low resolution. The way the light is catching those they are definitely like very small bubbles everywhere you look. Let's see if we can get a higher magnification. Well, if you had any doubt that they were bubbles, I think your doubts must have now disappeared. Let's just bring them into focus. So they're not very big, they're micro bubbles. We're halfway to achieving what we need to achieve. So now we're going to look at the extruded acrylic, where we used exactly the same parameters. And at 400, well, there are a few little bubbles in there, but not many. Most of it looks like it's granular in structure, you know, a bit like sand with a few bubbles in it. So this is a completely different texture.
So really the lesson here is very simple. You can't rush it. The best result is on extruded acrylic, and you don't need to go to the trouble on any of these of using tempera paint. Cut the middleman out and go straight for pure carbon black. Mix it with isopropyl alcohol, and there we go. These are the results you get. So I'm now going to cut the piece of video in using the CO2 laser, which shows you how big bubbles produce whiteness. Okay, we've produced some bubbles here as we saw, but they're micro bubbles and they don't jump at you as being white. This one is a lot more positive, and it has got no bubbles in it. We've just managed to impregnate the surface with carbon black. This stuff is clear and we can see through it. You can see what I've got here. This stuff is clear and you can see through it as well. It might seem far-fetched to say this, but effectively this is equivalent to water in every way possible. You can see through it, that's just one thing, but that's not the point that I'm making. The point is that this is like water in its solid state, ice. Take this above 0 degrees C and it turns to this liquid. If we take this stuff above 160 degrees C, it turns to liquid. If we push this stuff up to 100 degrees C, we know what happens to it. It boils and it vaporizes and turns to steam. Push this to 200 degrees C and it does exactly the same. It turns to vapor and you get acrylic steam coming off. And you know what happens if you put a cold surface under steam? It will recondense again. This is exactly what you see when you get all this white haze on the surface of your engravings. It's recondensed solid acrylic. Okay, so joke over. It is similar to water in many different ways. And I'm going to show you another way that it is very similar to water. Okay, now your eyes are very easily deceived. Colour is a wonderful thing if you understand how it works. But look at this. Absolutely clear water. And what have I just done? I've turned it white. How did I do that? Why is that white? Well, the answer is very simple when you think about it, because you know what I've done. I've created bubbles in there. And bubbles are like cat's eyes in the road. They reflect the light and refract the light in all sorts of different directions. What we see is a scattering of the light that's around us, white light. There is no chemical reaction going on in there, because the only way that this material disappears is by vaporization. So that colour is not coming from any change that we've made to the material. It's come about because we've done that. We've refracted and reflected the light in some strange way, usually with bubbles. So, what's the difference between these two materials that causes them to be different in the way in which they engrave? They both start off as methyl acrylate. It's just a molecule, okay? And you would see it as MMA. MMA on its own is useless for us. But what we do, we take these molecules and we put them through a process called polymerization. And basically that's a chemical process that I'm not going to get involved with, that basically joins all the single molecules together into a long chain so that they become a useful plastic. And then they become polymethyl acrylate. And that's what we buy, PMMA. Both of these materials are PMMA. So why are they acting differently? Well, the problem is really the way in which the PMMA the polymerization process is created and comes about. In the case of cast acrylic, we've got about 95% polymerization. That's the efficiency of the chains joining together, all the molecules joining together. But in the case of extruded acrylic, it's a little less efficient, and we've only got about 90% polymerization. So technically we've got two different materials here. Even though they're made from the same material base to start with, they're not the same. They might look the same, but the properties of them are different because of this change in the polymerization. Now the manufacturing process creates other small issues with it as well, but mainly it's this polymerization difference that gives us the main property differences between these two pieces of material. Can we make this cast white engraving also happen on extruded material? There is no reason why not, because look, bubbles are bubbles. The colour has got nothing to do with the material, as I said. It's all to do with what your eye perceives, the reflection of what you've done to this surface of this material that's caused it to give off whiteness. Okay, so we go and take a look at these under the microscope. What's causing the difference in these two colours?
Well, first of all, let's take a look at the cast acrylic. And here's what my engraving lines look like. A bit weird, aren't they? I'm right down to the, if you like, the base material now. And I'm now going to drop the table down so that we move out further and further and further. Now, can you see all those bubbles in there? Look at them. Hundreds of them. Everywhere you look, there's bubbles. Right, we're now up above the surface and we're going into fresh air. So if I change the magnification back a little bit, drop it off a little bit, we should see them a little bit clearer. But you can see that there's still, there's huge depth there. Look, there's a hole in the bottom, but even in the bottom here, look at the hole in the bottom, it's full of bubbles. And then I'll draw down and we'll pull out of the hole and we come up towards the surface of the material. And as we come up towards the surface of the material, look, bubbles, bubbles, everywhere bubbles. As I tried to explain to you before, that's the cause of all of our whiteness that we perceive. There is scattering of light everywhere in this material. Let's compare that with the extruded acrylic. We've got hardly any bubbles in there now. Look, we've got lots of lovely solid material, melted material that's not bubbles. Now, remember, these materials melt at about 160 degrees C. So they go on to boil at 200 degrees C. And the boiling action is the thing that's creating these bubbles. We're not seeing a mass of bubbles. We're seeing a few bubbles. Now, does that mean we're not heating it up hot enough? Probably. Or does it mean we're overheating it? I think it probably means that we're not heating it up enough. We need to find ways to create more bubbles in this particular material. We need completely different settings. Okay, well there we go. We've finished with acrylic engraving at the moment. We've experimented with that using 5 watts. In the next session we'll probably move on to glass, but before we do that we might try experimenting cutting black acrylic, because there's no way that we're going to cut clear acrylic, but we might be able to cut black acrylic, and we'll find out what we can do with black acrylic next time. So thanks for your time today, and we'll catch up with you in the next session.